So welcome to this review video on gases, chapter 10 out of the Brown-LeMay bursts in text. Please pause the video now to make sure that you have a piece of paper, pen or pencil in front of you, and a yellow periodic table with a bunch of equations on it. We're particularly going to be looking at the gases equations, so make sure you got one of those handy. And you might want a calculator to pause and work some problems too. Pause the video now. Gases, ladies and gentlemen. Gases, there are four factors that relate or determine the properties of a gas. They include pressure, volume, temperature, number of moles, or amount of gas. The relationships between these, when others of the variables are held constant, can be related in this way. Volume is inversely proportional to pressure. If volume goes up, the pressure goes down. You can remember that by the vice president. Temperature and volume, this is the television relationship. If one antenna goes up, the other one goes up. This is called a direct relationship. I should write these words down here. This is inverse, this is direct. Temperature and pressure can be remembered by the toilet paper. If the temperature goes down, the pressure goes down. This is a direct relationship once again. Remember, this is holding the other two variables constant. So if we're talking in terms of temperature and pressure, that means volume and number of moles of gas stay constant. If we're talking about temperature and volume, that means pressure and number of moles of gas stay constant. If we're talking about volume and pressure, that means temperature and number of moles of gas are held constant. And the last one is known as Avogadro's law. And this is volume and number of moles of gas, and this is also a direct relationship. If one goes up, the other one goes up. You can imagine that this makes sense. The more gas you have, the more volume you're going to have as long as pressure and temperature stay constant. These four relationships are actually given names. This is called Boyle's law, this is Charles' law, this is Gay-Lussac's law, and this is known as Avogadro's law. Graphically, you should know how these are represented with one another. And if we're holding the other variables constant, as pressure increases, in other words, as pressure goes this direction, remember volume goes down. And so we get a graph that looks something like this. Okay? An inverse graph. Volume and temperature are a direct relationship, and so as temperature goes up, volume goes up. Volume goes up, temperature goes up, and so it should be a straight line graph like this. Pressure and temperature, as pressure goes up, temperature goes up, and so we should get another straight line graph. And number of moles and volume are also a direct relationship, and so as number of moles of gas go up, so does volume. That's a direct relationship graph. So you'll notice the only one that's different than a straight line is the volume-pressure relationship, because that's an inverse graph, or inverse relationship. Equations, ladies and gentlemen, relate all of these, and we're going to take a look at them on this paper, because this is the one that you get on the actual AP exam. We're going to look closely at them in just a little bit. Pause the video now if you don't have these in front of you, because we're going to talk about how volume, pressure, temperature, and number of moles of gas are related together in various equation relationships. Just to start with, though, we can say that pressure and volume, once again, have an inverse relationship. So pressure times volume are equal to some constant n. Volume divided by temperature is equal to some constant, we'll call it K. Pressure and temperature are related, so pressure divided by temperature are equal to some constant, we'll call it Q. And N and V are directly related, so N divided by V are equal to some constant. Let's call it Z, just to use some kind of number. These small mini equations we never really have to use, because we can always just ask if one increases, what happens to the other. And qualitatively, these are the types of questions you're going to get, and you'll use the PV equals nRT relationship for something a little bit further. Gases are assumed to be at certain conditions, and one of the set conditions for gases are called standard temperature and pressure. Standard temperature and pressure are 0 degrees Celsius or 273 K, and we always want to work in Kelvin when we're working with gases, and also 1 atmosphere or 760 torr or 760 millimeters of mercury or 101.3 kilopascals. Or if you want to put this into something that we use for our tires, it's like 14.7 pounds per square inch. Not used on the AP exam very much. But these guys are. These guys are. And those are the ones that you should know indicate standard pressure for a set of gases. You'll notice that the standard temperature for gases is different from the standard temperature used in thermodynamics. As a matter of fact, I may as well talk about that now. In thermodynamics, it's assumed that you're at 25 degrees Celsius or 298 K. This is for thermodynamics. So when you're talking about delta G, delta S, or delta H, this is the standard temperature conditions for that. But in gases, the standard conditions are 273 or 0 degrees Celsius, something to keep separate in your mind. Lots of times in gases we talk about ideal gases. And I wanted to talk just a moment here about the differences and similarities between ideal and real gases. We make two major assumptions in gases to make them be ideal and therefore take equations and plunk them into them. First of all, we assume that the particles that make up the gas have no size. They have no size. And in other words, even though a molecule of N2 really technically does have a radius, and we've talked about it in other chapters, we just assume that it has no size comparatively to the entire sample of the gas. This, of course, is sometimes wrong, and that's why it's called an ideal gas, not an actual real gas. We also assume that when gas molecules collide with one another, they collide with what are called perfectly elastic collisions. In other words, no energy is lost or gained when a molecule collides with another molecule. This, of course, affects the pressure that the particles exert. And we assume that the pressure, as long as nothing else outside changes it, remains the same because these elastic collisions retain all the kinetic energy when they bounce off of each other and with the walls of their container. First of all, or last of all, we assume these two things about a gas. We assume that for a gas to be ideal, that it exists at a high temperature and a low pressure. Now these numbers, these are relative, of course, depending on what the substance is. But if we're talking about something like water vapor, for example, or water gas, we wouldn't want water to be at like 50 degrees Celsius, because if it was at 50 degrees Celsius, it would be mostly liquid as long as the volume and pressure were standard or normal, open to the atmosphere here on Earth. There would be some that's in the gas form, and we'll talk about that in a little bit too. But generally, we want the temperatures to be very high for the substance. Now, if we're talking about nitrogen gas at 50 degrees Celsius, that would be a high temperature for nitrogen, because nitrogen doesn't become a liquid until like negative 180 Celsius or something like that. And so it's relative depending on what you're talking about. But the reason we say high temperature is because we want it to be well beyond that temperature where it would turn into a liquid. Lastly, we want it to be low pressure. Obviously, if you take something like nitrogen and you squish it inside of a container, this is a piston here pushing down that nitrogen gas, you're going to turn it from a gas into a liquid. Then the gas laws don't apply to it anymore. When something's a liquid or a solid, it's not a gas anymore, and you can't call it an ideal or a real gas because it's no longer a gas. So we assume those two things, high temperatures and low pressures, or we want those conditions when we're talking about gases. All right? Here's one that actually went along with a little song that we had in class, that equal volumes of gases, for example, if I had 1 liter and 1 liter of two different gases, and if they're at the same temperature, 273 K and 273 K, and they're at the same pressure, say 1 atmosphere and 1 atmosphere, then we conclude that they have the same number of molecules. Okay, and these are the three relationships that we just talked about, or I'm sorry, the four, where this is volume, temperature, pressure, and number of moles of gas. These four things are all interrelated, and you can talk about each one individually if you're holding the other three constant. And we'll look at a sample problem in a little bit where we have two gases and they have a lot of these things same, but one thing's different, and you can make a conclusion about that. Equal volumes of gases at the same temp and pressure have the same number of molecules. All right, we're going to talk about equations as I promised, and we're going to talk about the manipulation of some of the equations. First of all, let's zoom in on the equations that you'll get on the AP exam, and let's just go through them really quick because these describe ideal gases. The first one, of course, at the very tip top is the ideal gas equation itself, and this is PV equals nRT, where pressure is P, V is volume, N is the number of moles of gas, and R is known as the universal gas constant. The universal gas constant has three different values given on the AP exam, depending on what units the pressure is in. Depends on what units the pressure, and T, of course, is temperature, and it has to be in Kelvin. Let's look at where the R is located on here. I'm just going to zoom out so I can show you where it's located, because it's not underneath the normal gases, liquids, and solids. Go across the table over here and go to the lower right-hand corner. You can see underneath constants here are the different gas constants. You can see there are 3 different ones with different units. Here's R as 8.31. They have it as joules per mole Kelvin. Okay, this is also the unit that you would use for kilopascals for pressure. This is 0.0821, which is liters atmospheres. So this is the units or the gas constant you would use for atmospheres. And then this is 62.4 liters times torr per mole Kelvin. And this is also the constant you would use if you were in millimeters of mercury. So depending whether it's kilopascals, atmospheres, torr, or millimeters of mercury, there are 3 different gas constants that you don't need to memorize, but you need to know that they exist, so you choose the right one. So you choose the right one based on the units that they give you in a particular problem. Okay, let's take a look back here at the equations again. We talked about ideal versus real gases. Well, scientists have taken into account these problems with real gases, that actual gas molecules do take up a small amount of space. This space, of course, is called volume. And so this equation right here is called the real gas equation. And it looks like PV equals nRT, except it corrects for 2 problems. The first one is the size of the actual molecules, and that's what this NB part corrects for. And then the n squared times A divided by V right here, that takes into the account that the particles actually do collide and gain or lose a little bit of energy, adjusting for the pressure of the gas particles for reals, in real gases. So there hasn't been an equation, a calculation that's actually used this in many, many years on the exam, but there have been some questions qualitatively about what 2 factors are taken into account in real gases that are assumed to be constant in ideal gases. And you can figure those out from here. One involves volume and one involves pressure, and these are the corrections that are made. Next equation is the partial pressure, taking partial pressure into account. And this equation right here is for mole fraction. Mole fraction, that's this x with a little a, is equal to the moles of a part divided by the moles of a whole thing. So part divided by whole gives you the fraction. Notice it has no units because the moles cancel, and it turns out to be a decimal. They call it a mole fraction, but usually you write it as a decimal. And you can find the partial pressure of the gas by taking the total pressure of the gas times the mole fraction of that gas. Next is another partial pressure equation. This is called Dalton's law of partial pressures, where it says the total pressure of a sample of gas is equal to the partial pressures of each gas that makes up that entire sample of a gas. This is the moles equation. Moles are equal to mass divided by molar mass from the periodic table. This is atom up on the periodic table. This is mass in grams, and this is moles. Remember, molar mass is given in grams per mole. Mass, of course, is in grams. And you can see that the grams will cancel with the grams, and you'll get 1 over moles, which will give you N right here. This is Kelvin converting to Celsius, or Celsius converted to Kelvin. Kelvin is equal to Celsius plus 273. This is a conglomeration, and it is sometimes called the combined gas law equation. P1 V1 divided by T1 is equal to P2 V2 divided by T2. This can also simply be taken into account by what we talked about before, how volume and pressure have a relationship, temperature and volume have a relationship, temperature and pressure have a relationship, and N and V have a relationship. And remember, these are all direct. The TV is direct, and the volume and pressure are indirect, which this equation takes into account. If you like plug and chug, this is good. This will give you a good way to say this one's getting bigger, so this one's got to get smaller. So multiply by a ratio to make it get bigger or smaller. This is the density equation, where density is equal to mass divided by volume, except they use a capital D, not a lowercase d. So this is actually just the density triangle right here. This is the speed, known as the root mean square speed of a gas particle. We usually don't use this first equation, but the second one we do is equal to the square root of 3RT divided by molar mass. And so if you're comparing the speed of two gas samples, if they're at the same temperature, you can just know that they're inversely proportional to their molar mass. Because you can see capital M down here stands for molar mass. This stands for speed. So the bigger the particle, the slower the speed. See how they're inversely related to each other? Or you could say the faster the speed, the slower the larger the particle, as long as the temperature remains the same for those samples of gas. Kinetic energy, this is kinetic energy per molecule, and this is kinetic energy per mole of substance. This is equal to 3 halves RT. R, remember, is the universal gas constant. T's got to be the Kelvin temperature. This is known as Dalton's law of effusion, or Dalton's law of diffusion. It says that the rate of diffusion of one gas compared to the rate of diffusion of another gas is inversely proportional to the molar masses of those gas. See how it's R1 over R2 is equal to molar mass of 2 over molar mass of 1, and it's square rooted there as well. Then there's some last equations down here, and those have to do with solutions, and we'll talk about those in Chapter 13. Those are the equations that you need to know. Here's one manipulation of an equation back on our notes page right here. One manipulation of equation that did come up in a couple of past AP exams. First of all, you know that density is equal to mass divided by volume, and you also know that PV equals nRT, and we also know that moles are equal to mass divided by molar mass. All three of these equations are given on the periodic table right here. PV equals nRT at the top. Here's the moles equation, and then I pointed out the density triangle equation in there as well. Well, we can use these three equations to solve PV equal nRT for density. Solve PV equals nRT for density. So in for n right here, I can put mass divided by molar mass. This now becomes P equals mass divided by molar mass times RT. Doing a little bit of manipulation and rearrangement, we can take our MMRT, and I'm going to multiply this side of the equation by MM divided by RT, which means I need to do the same thing to this side. Multiply by MM divided by RT. Notice the MM and the RT now cancel with one another over here. And lastly, I'm going to divide this side of the equation by volume, which means I need to divide this side of the equation by volume. The V's cancel, and I'm now left with capital M, which is molar mass, times pressure, divided by R, times T, and this is equal to M divided by V. Now, M divided by V is given a different name. What do we call mass divided by volume? Well, of course, we call it density. And so density is equal to military police over rapid transit, or molar mass times pressure divided by the universal gas constant times temperature in Kelvin. So manipulating this equation right here using the definition for moles can allow you to find the density of a gas by knowing the molar mass, the pressure, and the temperature. All right? One more definition. Temperature is defined as the average kinetic energy of the gas particles, and therefore temperature is directly proportional to kinetic energy. And you saw this actually in one of our equations here, how kinetic energy per mole right here, I'll zoom in on it again, is equal to 3 halves RT. So you can see that kinetic energy is directly proportional to temperature. And if you forgot what kinetic energy is, that's the energy of moving things. And of course, we assume that gas particles are always in constant motion, crashing into each other and their surroundings. The higher the temperature, the higher the kinetic energy. The lower the temperature, the lower the kinetic energy. Can you remember that relationship? Sure. If you just take a look at the periodic table, it will give it to you. Kinetic energy is equal to 1/2 mu squared per molecule, 3 halves RT per mole of gas, which you saw on the periodic table as well. Lastly, speed. Speed of a gas particle is actually found by taking what's called the root mean square average. The root mean square, average, I guess, because they usually put a little line over here meaning average. And this is equal to the square root of 3RT over capital M. And so the relationship is that the bigger the gas particle, the slower the speed, or the smaller the gas particle, the larger the speed. And therefore, it gives you a good chance to see how size can help or deter the speed of a gas particle. Well, let's take a look at some recent AP exams, and let's look at their questions and go through some of them. I'm going to start with 2004. We'll start at the top here, and we'll just work through a portion of this exam. So write down on your sheet the 2004 released exam. This is question 8, 2004, question 8. Pause the video now if you want to give that problem a try first, and then you can see me actually work the problem after it. I'm not going to do A, B, or C because those have to do with drawing Lewis dot structures and identifying shapes, and that was in chapters 8 and 9. And then this one right here, identifying a pH, that's actually chapter 17. But, you know, it's a good time to review everything because obviously all of these things are going to end up in one question for you too. And so you can see that carbon dioxide, when it dissolves in water, forms this H2CO3. This is a good reaction to remember. And that's, of course, a weak acid, and so the pH is less than 7. Then let's get into the gas laws question right here, and this is question D. It says 1 mole of a sample of CO2 is heated at constant pressure. On the graph below, sketch the expected plot. Sketch the expected plot of volume versus temperature as the gas is heated. So as temperature goes up, what happens to the volume of the gas? Well, remember back to what we just talked about. Temperature and volume, remember, have what's called a direct relationship. One goes up, the other goes up. So as temperature goes up, the volume of a gas goes up as long as we're at constant pressure. And so I'd have to draw a line like this, indicating that as temperature goes up, volume goes up. Graph should have a straight line with a positive slope, is what they said on the scoring guidelines that year. Let's turn to the next page. Here it says samples of CO and CO2 are placed in 1 liter containers in the conditions indicated on the diagram below. So here we have a diagram, and we know that this is 1 liter of CO gas. This is 1 liter of CO2 gas. This one's at 25 degrees Celsius. This one's at 25 degrees Celsius. This one's at 1 atmosphere, and this one's at 2 atmospheres. And I always think it helps to make a table of what you're organizing your data to be. Temperature, volume, pressure, number of moles of gas. Temperature, volume, pressure, number of moles of gas, especially if they're going to ask you a number of questions about a particular gas. And in this case, we know that the temperatures are 25 or 298. 298. The volumes are 1 liter and 1 liter. The pressures right here are 2 atmospheres, and this one's 1 atmosphere. So far the only thing different are the pressures of these gases. And the number of moles, we're not told how much each gas contains, and I'll bet that's going to be one of their questions in a little while. First of all, indicate whether the average kinetic energy of CO molecules is greater than, less than, or equal to the average kinetic energy of the CO molecules. So is CO2's average kinetic energy the same as CO or not? Well, remember that kinetic energy is directly proportional to temperature. So how are the temperatures compared to each other? Well, if the temperatures are equal, then kinetic energies are equal. Because remember, kinetic energy is equal to 3/2 RT. 3/2 RT. And 3/2 would be the same for both gases. R would be the same for both gases. So as long as the temperature is constant or the same, the kinetic energy is also the same. And it doesn't matter what kind of gas we have, as long as it is a gas. Okay? So their answer, the average kinetic energy is the same for both samples because the temperature is the same. Question number 2, indicate whether the root mean square speed of the CO2 molecules is greater than, less than, or equal to the root mean square of the CO molecules. Justify your answer. Well, remember the equation for root mean square was square root of 3RT over capital M. Now, if the molecules are at the same temperature, which they are, 298, we said that, and the R's and the 3's are the same, what is the one thing that is the factor that determines the speed of a substance as far as a gas goes? Well, it's molar mass, right? The bigger the mass, the slower the speed. So we would assume that carbon dioxide moves slower or is less than. The root mean square for CO2 is lower than the root mean square speed for CO. The molar mass of CO2 is higher than the molar mass of CO. The root mean square is inversely proportional. You like that? They like that word. You could use that too. Lastly, indicate whether the number of CO2 molecules is greater than, equal to, or less than the number of CO molecules. Justify your answer. Well, now you can use your relationships that you had up here between temperatures being the same, volume being the same, but pressures are different. So the only thing really factoring in to change the number of moles of gas is not temperature, because they're the same, not volume, because they're the same, but pressure. Well, this one has higher pressure. What's causing that higher pressure? Well, it's not volume, and it's not temperature. So it must be number of moles of gas. So there must be more moles of gas here than here, because it's causing more pressure. More particles, more collisions, therefore more pressure. Let's read their answer. There are fewer CO2 molecules than CO molecules. The CO2 molecules exert half the pressure of the CO molecules, so there must be half as many molecules. And that's what we predicted, was that there were more molecules up here of CO. As a matter of fact, there's twice as many. Okay, that's one problem. Let's take a look at another. This is just one portion of a test from 2004 again. Let's take a look at just the very first part of question number 2 from 2004. In this question, they say, iron reacts with oxygen, produce iron oxide. 75-gram sample is mixed with 11 grams. Calculate the number of moles of each of the following. So first of all, we're given the number of grams of iron, and so you go from grams to moles right here. Then secondly, they ask for the number of moles of oxygen. Well, they give us some info up here. They tell us the volume of oxygen, they tell us the pressure, and they tell us the temperature. Now this, straight up here, looks like it's more going to be a thermochemical equation, because they give us a delta H. They ask us a question about converting to moles from grams. But now all of a sudden they throw us a curveball. They want us to be able to use gas laws somewhere else in a question. And as a matter of fact, this turns out to be a PV equals nRT question, because I know the volume, the temperature, and the pressure. I can solve for the number of moles of gas, and using 0.0821 atmospheres for my R, I get a number of moles of 1.25. Anticipate this, that they'll ask questions that really don't have anything to do with gases, but they'll expect you to use PV equals nRT or some other gas laws equation to find some substance. The rest of the problem has to do with limiting reagents, and it has to do with H and things like that. They stick a gas laws question in there to find out if you knew something about gas laws as well. Let's see how they did that again in another problem. Okay, here's 2003 question number 2. This is more of a straight gas laws, but it does relate a lot of different things. A rigid 5-liter container contains 24.5 grams of nitrogen and 28 grams of oxygen. Calculate the total pressure in atmospheres of the gas mixture of the cylinder at 298. Well, I know a volume, I know masses right here, and I know a temperature. So organize your data: pressure, temperature, volume, number of moles of gas. Remember, those are the factors. Pressure is 5 liters. I know the temperature is 298 K, and the volume is unknown. Oh no, 5 liters. Whoops, I put the pressure in the wrong place. It says calculate the total pressure. Well, I should have put a question mark here. I thought that was volume first. My bad. Anyway, the volume is 5 liters right here. The temperature is 298. The pressure, I don't know. And number of moles. Ooh, do I know the number of moles of gas in there? Does it tell me number of moles? No, but it tells me there are 24.5 grams of nitrogen and that there are 28 grams of oxygen. Guess what I could find from that? Yeah, you guessed it, I could find the moles. So convert to moles of nitrogen and moles of oxygen. Turns out I have the same number of moles, 0.875. add those together and plop them into PV equals nRT, because that's my total moles of gas, 0.875 plus 0.875, and I end up with 8.5 atmospheres. 2 points for that. But there's a good use of PV equals nRT. All right, next question. The temperature of the gas mixture in the cylinder is decreased to 280. Calculate the mole fraction of N2 in the cylinder. Okay, now this really doesn't have anything to do with temperature, but remember mole fraction is part divided by whole. So I'll take the mole fraction of N2 and I'll take my part of moles, that's N2, which is 0.875, and divide it by the whole number of moles that are in there, which of course is 0.875 plus 0.875, and then write it as a decimal, and I get 0.5 for my mole fraction. Next part of the question goes on to ask more gas laws stuff. It's a fun gas laws problem. Hope you get one like this. The partial pressure in atmospheres of N2 in the cylinder. Okay, well, now that we know the mole fraction of it, we could do several different ways, and they list 3 different ways to find the partial pressure of N2. First, you could just use PV equals nRT, okay? And then you could find the total pressure inside the container and multiply it by the mole fraction of N2 that you found. So it's half of 8 atmospheres, which would be 4. Or you could use PV equals nRT directly just to calculate the pressure of nitrogen by putting in the number of moles of nitrogen times RT divided by V, and you get 4 moles that way as well. Or you could use one of these ideal gas equations right here and then the mole fraction to find 4 moles of 4 atmospheres of pressure as well. Any one of those ways is acceptable, and they all get to the same way, a different way. Next, the cylinder develops a pinhole-sized leak, and some of the gaseous mixture escapes. Would the ratio of moles of N2 to moles of O2 in the cylinder increase, decrease, or remain the same? Now, the equation we're going to use here is known as Graham's law. R1 divided by R2 is inversely proportional to the square root of the molar mass of 2 to the molar mass of 1. And so it wants to know what would happen to the ratio of the moles of N2 to the ratio of moles of O2. Okay? So we're looking for this fractional number. Would it get bigger, larger, larger, smaller, or remain the same? The ratio of moles of N2 to O2 would decrease. N2 will effuse faster than O2 because N2 has a lower molar mass. Thus, in the cylinder, the moles of N2 would decrease faster than the moles of O2. And we can see this by saying, okay, I want to know what's going to happen to the rate of effusion of N2. Well, I put N2's molar mass down here, it's 28. And then I put the molar mass of O2 up right here, which would be 32. And so I can see that this would be a number larger than 1. And so N2 versus O2 would have a rate of effusion that's faster than O2. Now, another way to do this is simply to look at the speed of the molecules, too. So remember we said or speed of the molecules is equal to 3RT divided by capital M square rooted. And we said that the faster the molecule, the smaller the molecule. Or the smaller the molecule, the faster it is. And of course, the faster it moves, the faster it effuses. And so the smaller molecule is N2, 28. And so it will diffuse or effuse faster. It'll have a speedier motion than the other one. That's another way to understand that. A different rigid container contains 0.17 moles of nitrogen and 0.17 mole sample of oxygen. Notice, same number of moles. Okay? At 298, it's added to the cylinder, and assuming that we're going to produce NO2, it says. So write the balanced equation. There's the balanced equation of what we're going to form, not a really gas laws problem. And then calculate the total pressure in atmosphere in the cylinder after the reaction is complete. So now we have a stoichiometry experiment to do here. So they did a nice table here where they said this is my number of moles to start with. This is my number of moles to start with. Notice it's a 2-to-1 ratio. So obviously then nitrogen monoxide is my limiter. I end up with 0 of that. I end up with 0.088 moles of oxygen left. And since it's a 2-to-2 ratio, I produce 0.176 moles of this. Now, if I want to know the total pressure inside of there, I have to take these number of moles and add them. And when I add those together, then I can put it into PV equals nRT. And so I end up with 1.29 atmospheres, plugging it into perv. Great perv question, gas laws question back in 2003. Let's look at a couple of more. These are some portions. This happened in 2002. This is 2002, question number 3. First of all, it said write the balanced equation for the combustion of pentane. There's the combustion of pentane. Great question. Easy to balance, a weak animal for you to get. Second of all, what volume of dry carbon dioxide measured at a temperature, a pressure, and we've given a number of grams of pentane. Another one where we're going to have to use some gas laws to do something stoichiometrically. So step number 1, find the number of moles of this. What's the relationship between this and carbon dioxide? 5-to-1. Once I know the number of moles here, now I can put it into PV equals nRT, and I could solve for the volume by dividing both sides by P. I know my pressure. I know my temperature, 25 degrees Celsius, but make sure it's 298 K. I know my N right here because I figured it out stoichiometrically. And here's the actual math. It turns out to be 4.1 liters. Now, the next part of the problem doesn't ask about a gas law, but you can see that this part interwove a gas law into a balanced equation and then a combustion reaction using delta H. There's a little more gas laws on the next page, so let's take a look at that. This one said, under identical conditions, a sample of an unknown gas effuses into a vacuum twice the rate of the sample of pentane. Calculate the molar mass. Well, here's another one where we're going to take a look at the rate of effusion of one gas versus the rate of effusion of another. And remember, that's inversely proportional to its molar masses, the square root of its molar masses. So we can say that the rate of the unknown gas compared to the rate of C5H12 is inversely proportional to the molar mass of the C5H12 to the molar mass of the unknown. See how I set that up? Okay, and then we can say that it's twice as fast, so 2 times the rate of C5H12. The unknown diffuses at 2 times that. So for the rate of unknown, I could put in 2 times the rate of C5H12. Okay, so now I can say 2 is equal to, because the rates then will cancel, 72.15 divided by molar mass. Solve for the molar mass, and it ends up as 4. And then, this equals 4, and then the molar, squaring both sides. The molar mass of the unknown turns out to be 18 grams, and that's the molar mass of the unknown gas. See how you can use this to determine what an unknown gas is. I'm not surprised to see one of these questions show up. Then lastly, they ask a question in this one about an isomer of pentane. And if you haven't watched if you don't remember anything about the organic unit, this is the type of question that has potential to show up. Remember, to make an isomer, you break a bond, and then you reconnect it somewhere else where it's not just part of the longest chain. Here are a couple of examples of isomers. Notice they broke the chain and made it not be continuous. All right, let's take a look at one more, no, maybe 2. This is a gas laws problem from 2009, and it was kind of a lab problem. They were assigned to find the molar mass of an unknown gas. The student measured the mass of a sealed 830 43 milliliter rigid flask containing dry air, flushed the gas with the unknown gas, resealed it, measured again. The air and the gas were at 23 and 270 torr. The data for the experiment are below. So here's volume, mass, mass of the unknown gas. Calculate the mass in grams of the dry air in the sealed flask, and they give you the density. Remember, density is equal to mass divided by volume. That could definitely help you. So here is the mass of the dry air. Then they say calculate the mass in grams of the sealed flask itself. So you subtract out the dry air from the flask. Notice this one, you don't really have to know anything about chemistry. You just have to know that a flask with air in it weighs more than a flask without air in it, and subtract out that air. Calculate in grams the unknown gas that was added to the sealed flask. So now you're going to do some more subtraction of the gas and flask minus the empty flask. And so you have 1.37 grams of the unknown gas that are in the flask. Okay? Using the information above, calculate the value of the molar mass of the unknown gas. And you have lots of data here. So PV equals mass divided by molar mass times RT probably becomes a realistic thing to use. And you can see right here they found the number of moles first rather than using this big equation. And then they put it into the moles equation to get the molar mass of 40.1. You could also solve it using the density equation that we talked about before. And there you go is your molar mass question. Let's look at another one that was similar to that. This one occurred in 2009 as well, but it was on the Form B question, Form B exam. So this was H2O2 decomposes. O2 produced was collected in an inverted graduated tube over water at 24 degrees Celsius when the water levels inside and outside the tube are the same. The atmospheric pressure in the lab was the equilibrium vapor pressure of water at 23.4 Celsius is 21.6 torr. First of all, calculate the pressure and torr of oxygen inside the gas collection tube. The first thing I'd do with this is organize all the data they give me, because they give me so much stuff up here. Take your time and organize the data. Don't just rush into doing it. Write down what the mass of the H2O2 was. Write down what is the temperature of this. What is the vapor pressure of the water at 23.4 degrees Celsius, which is 21.6 torr. Okay, write down the volume, which is 182.4 milliliters. The temperature was 23.4 degrees Celsius, which I'd stick to Kelvin right away. Organize that data. Now let's take a look at how they solved it. First of all, this was just a partial pressure question because inside the container there was some water gas, and they subtracted the water gas from the actual gas. Remember, it gave us the partial pressure of the water vapor pressure. So you subtract that out. Secondly, number of moles of O2 produced in the reaction. Well, now that we know the pressure of just the O2, and we know the temperature that it was at, and we know the volume that it contained in, now we could find the moles using PV equals nRT. So using PV equals nRT, we end up with 7.3 times 10 to the negative third moles. Calculate the mass in grams of H2O2 that decomposed. Well, now it's a stoichiometry problem, and you need to go from moles of O2, which we got right here, 2-to-1 ratio, 34 grams in a mole, and we get the grams of H2O2. Calculate the percent by mass of H2O2 in the original aqueous sample. Now we take part divided by whole. Part that's H2O2 divided by the original sample times 100%, 7.15. On the back side, they ask a couple oxidation reduction questions, and that pretty much does it for the gas laws part of that question. So, once again, to summarize gas laws stuff, here are the equations. Know what they mean. Know what the variables are. Know where the R gas constants are on the periodic table. get used to using just a portion of the gas laws like they did in many of these questions, where they're not all just straight gas law questions, but they'll ask you one or two things. And lastly, the number one thing I could say when you're doing these problems is the very first and the most important thing you can do is organize all the data that they give you, like I did right here with mass, temperature, vapor pressure, volume, number of moles of gas that they give you, and make sure that you're using the Kelvin temperatures and relating all the different factors, pressure, temperature, volume, and number of moles of gas to each other. Good luck on your gas law problems.